Is it with sound?
Sounds
Yes.
beautiful.
Yes, it is.
Mm-hmm.
Join us for Optica Online Industry Meeting on Tuesday, November 19th at 10 a.m. Eastern, 4 p.m. in Central Europe. And this is a big one. Traditionally, LiDAR has been one of the most popular topics. For 90 minutes, we explore the current business opportunities in LiDAR, as this is now one of the most unpredictable markets. I believe that the biggest decision regarding 3D sensing in robotics and automotive is whether to say yes or no to LiDAR. Tesla said no 3 years ago, as they believe that 2D cameras can do the job for automotive. However, for Elon Musk, SpaceX is different.
SpaceX Dragon uses LiDAR to navigate to the space station and dock. Not only that, SpaceX developed its own LiDAR from scratch to do that, and I spearheaded that effort personally. Because in that scenario, LiDAR makes sense, and in cars, it's friggin' stupid. It's expensive and unnecessary, and as Andre was saying, once you solve vision, it's worthless.
Other companies like Continental in automotive or John Deere in heavy machinery have invested deeply.
Today we are testing our HRL131 long-range LiDAR, which we developed together with our partner AI. And this LiDAR is developed to detect, for example, lost cargo, the tire, for example, that lies on the highway.
So what optics and photonics do those Continental and John Deeres of the world need? Investors are clearly confident that the LiDAR market is expected to grow to $2.3 billion by 2026. Despite some uncertainties, I think we should be optimistic. There's increasing adoption in domestic equipment, autonomous vehicles, particularly in Asia, along with applications in aerial mapping, defense, infrastructure monitoring, robotic vision, and environmental monitoring. And the biggest trend in LiDAR is the incorporation of AI, providing the system with an AI-educated guess, allowing them to react appropriately depending on what the object is. Our online meeting will showcase real-world end-user cases. Here are contributions from Continental, Robotics, John Deere, Lumotive, Optica, Scramblux, and many more. Actually, about 500 people already registered to be in the Zoom room. If you are active in LiDAR, join the list. And now, let's go live. Dr. Olga Ras, Director of Optical Systems at Optica. The floor and the attention of everyone is yours.
Hello, everyone. And now we're going live. Thank you, everyone, for joining this amazing meeting on the LiDAR. And it's my honor and pleasure to welcome actually so many excellent speakers to the event and also so many visitors and attendees. And just as Jose told us, today we're going to discuss the amazing topic of LiDAR and its applications across automotive, construction and agriculture, and also vision. Let's see where the LiDAR is go, where maybe it's no go, and just what are the trends, how we can adjust and look forward. And I would like to remind you that we are driving this meeting. It's an online Optica online industry meeting. And I just need to share my slide for the moment, sorry. And we are here with actually 10 speakers representing all the, I cannot do it simultaneously. All right. We're here in this meeting with several of the main end users and solution providers for this technology. Let me tell you, so we are here together with the system integrators, such as Continental and John Deere and Robotics, and together with the solution providers from Lumotive, Optica, IMEC, OIV, Scramblux, Excel, and NextCorp's Luminate. Or our solution providers are Optica corporate members, and this gives them a unique opportunity to present their solution here live to all of you, all of the system integrators, and now nearly 150 attendees in the Zoom room. So if you want to have an opportunity to present your solution, join us. Check us out at the optica.org industry or write a direct email to me or to Jose. And I also would like to welcome everyone who watches our live in YouTube. I would like to remind everyone that this meeting is live streamed over the YouTube. So YouTubers, hello to everyone. Just a little reminder how the meeting operates. So we have a chat. If you have questions to any one of the speakers, please don't hesitate to ask your questions. It's not a webinar, it's a seminar. We want to hear your voices, your opinions, your questions. And with this, I would like to start it and kick it off. And as already Jose mentioned in his introduction, the LiDAR seems to be, especially in the last couple of years, became quite a volatile market. It decreases in one part of the world, it increases on the other. And many of us, the first thing what we think when we hear LiDAR is, of course, autonomous driving, right? It all started with the Tesla saying, okay, this is the LiDAR is lame. Is it? Is it really not? And we have actually a couple of the speakers that are today joining us live from the DVN, which is Drive and Vision News event taking place on LiDAR, and we will later hear their first-hand impressions. But nevertheless, the first thing and the first speaker I would like to invite to the floor, as well already announced by the Jose, is Heiko Lepin from the Continental, working really on the LiDARs in the automotive applications and autonomous drivings. Heiko, how are you doing? Where are you joining us? From where are you joining us today?
Hey, hello everyone. I'm glad to be here. I'm glad to be invited to give you our view on LiDAR and LiDAR future. I'm joining you from my snowy home office in Lindau, Germany. Yeah, it's my pleasure to give you our view. I promised to keep the presentation short so that we have more time for interesting questions.
Then the floor and attention of everyone is yours. Please share your presentation and your ideas.
All right. Hope you can see my presentation.
We see it crystal clear.
All right. So with no further ado, let's jump into this right away. What's going on here? Here we go. Okay, so a few words about Continental. I think I cannot avoid those. Continental autonomous mobility is, of course, has a long track of record when it comes to LiDAR development and ADAS sensorics. A few words: we have delivered more than 200 million sensor units for ADAS and autonomous driving, mainly for ADAS. That be radars, cameras, LiDARs, AD control units, which is central ECUs. We deliver to 25 OEMs, 50 brands, more than 300 different models. So there's a huge portfolio of sensors that we deliver to enable autonomous driving. But today, of course, we will focus solely on the LiDAR, which is also the area where I'm most active. Jose already mentioned that LiDAR is a quite unpredictable market. So I chose to give you a little insight into what we've done and what we've tried in the last 20 years, or more than 20 years, almost 25 years actually. And here's a few products that we developed in the field of LiDAR, and there's all sort of technologies here. So we started with scanning LiDARs, which use like a voice coil to elongate or to change the viewing direction of the sensor. We did sensors like this one down here, which is we use a spinning prism or a spinning polygon. We build flash type LiDARs, or we develop flash type LiDARs, both with like the one down here with a specific OEM specifically developed components for this use case, but we also develop flash LiDARs like these ones up here, which are built only from off-the-shelf components. We did flash LiDARs like this one with very, very specific components. We did scanning LiDARs using MEMS mirrors, and also we have developed technologies based on VCSEL SPAD. So you can see there's a huge portfolio, and it's really, really unclear which is the right solution. So we try to stay ahead of all the different technologies and be able to master all of these technologies. I would like to introduce you to the most recent developments we've done in this area. And this again emphasizes Jose's words on the diversity of the market. And really, it is diverse. Yeah, we have developed a mid-range product with a 120-degree field of view, which is a full frame flash. So it captures the whole image at once. So there's no motion blur or anything like that, and every pixel is like timed equally. That can be very interesting for very high-speed situations when a car, for example, is quickly moving in a roundabout or a very, very dense and a complicated situation like a parking lot. It's a full frame flash. It uses a DPSS solid state laser, so it's a very, very unusual type of LiDAR. It uses in-gas detector array. Yeah, and it's really it's sort of mid-range product for highly dynamic situations. And then there's a long-range product which we developed with a very configurable field of view, which is like on in situ or online changeable. So it could act as a long-range narrow field or a mid-range wide field of view sensor. It uses MEMS scanners, 2D MEMS scanners. It uses a 1550 nanometer fiber laser. So again, a very different laser technology. It uses a 2D germanium detector array, kind of similar to the one we've seen in the first product. And then there's a third category of products which we have developed, or which we have started to develop actually, which is a short-range product. It has a very, very wide field of view, and we have demonstrated up to 180-degree field of view. It uses a segmented flash approach, which is based on a VCSEL laser and a SPAD detector array. And it's designed to be like very, very low cost. Yeah. So you see there's a huge variety of different solutions, and it's hard to say which solution will dominate the market. And maybe there is no solution that might dominate the market in the future. Maybe all of these solutions find their space in the automotive market. But this is kind of the snapshot of what is today. And I would like to show you, or I would like to introduce you to our considerations of how this market could evolve. So this is a kind of busy slide, and I would like to explain it to you. What you see in the middle, I would like to start here in the middle with a blue triangle. So this is today's high performance long range LiDAR, which is oftentimes fiber laser based, which is usually a DTOF 1550 nanometer technology. It usually uses some sort of scanning, right? Either polygons or galvos or MEMS. And there's a couple of companies active in this field. And this is just a selection. So this is by far not complete, right? But this is like the long-range high-performance product that we see in the market today. And then there's other technologies, emerging technologies. Here on the low end, just like the products that I showed before, there's VCSEL SPAD technology, which is fully, kind of fully solid state, very high integrated solution, which uses a shorter wavelength, 905, 940 nanometer, which is also cheaper from a technology perspective. Usually flash or segmented flash. And again, there's a lot of players in here. This is today kind of the lower cost, lower performance technology. But with increasing volume, once these products go to market, the performance will increase. Yeah, with every generation, the performance will increase. So we believe that these products will eat away market from the long-range LiDAR, which we see today. And then there is another technology, another emerging technology, maybe not as far developed as VCSEL SPAD, but it's very heavily developing at the moment, and that is the group of coherent photonically integrated LiDARs, based on photonic integration, usually using some coherent modulation method like FMCW or PNCW or other technologies. It will probably be in the 1550 nanometer, 1310 nanometer regime. But for a very long time, very long foreseeable time, it's going to be a scanning technology. So it's going to be, it's not going to be flash. It's not going to be 100% integrated, but maybe integration will increase. So this is a very high performance, because complicated and costly, high performance and high cost technology. Also, there's a lot of players in this field, and by growing market share or growing market penetration, it will be possible to drive down the cost of this technology. So this technology will eat away from today's long-range LiDAR as well, right? And there is the question arises, where is the point where these technologies dominate the market? And also there's a question, where is this point where these technology meets, right? Is it here in the middle? Is it more up here, or is it more down there? We don't know yet. So that's also the reason why we are very closely monitoring these two technologies. If we look near future, like the next couple of years, this is a slide I with from Yole, which Yole presented a month ago in Paris at the CI Vision conference. They allowed me to share this slide here with you guys. If you look at the market, how the market in LiDAR, automotive LiDAR looks like, you see that today, 2024, the hybrid LiDAR is something that really dominates the market today. Hybrid LiDAR means either it uses a spinning polygon or something similar. And there's a reasonable share of MEMS solutions, and flash LiDAR is almost not it doesn't play a role at all. And all of these LiDARs are of the direct time of flight type, incoherent sensing. If we look to 2029, or let's say if we look into near future, if these numbers are completely correct, no one can tell. Yeah, so this is just a guess of what's going to happen. So around 2030, let's say, the flash type will increase, will eat away from the hybrid solid state LiDAR. And also you see that FMCW is just starting to emerge. And that very well aligns with the view on the market that we have. FMCW is going to be something that will happen, but it will take some time until it happens. And flash LiDAR is going to pick up and going to eat away market from the hybrid solid state LiDAR. And again, thank you to Yole letting me share this slide. So that brings me already to the end of the presentation. Again, I said I keep it short so that we have time for questions. So there are many LiDAR technologies out there competing for the automotive market. And two particular technologies which we see very, very promising is the VCSEL SPAD technology, which emerges from the low performance segment, and the photonically integrated LiDAR, which will be seen maybe around 2030, but that will emerge from the high performance, high cost segment, and will penetrate into the more affordable segment later. We closely monitor all these technologies, and we try to stay ahead of these technologies as much as possible. And if that's something where you think you can help us, please get in contact with us.
Well, that's an excellent last touch for the presentation. But Heiko, if you're really being specific, tell us like what type of the technologies, for instance, or I don't know, sensors, lasers, maybe scanning systems that you're specifically looking at.
Okay, so we work on VCSEL SPAD solution, and we work on photonically integrated solutions. Yeah, VCSEL SPAD is something that is more near term, and the photonic integration is something that's more long term. So there's much more room for collaboration in the long-term market, obviously. Yeah. So our vision is a fully integrated, fully solid state, photonically integrated LiDAR. That means aside from the integration of the laser and the modulation and the receiving part, we also hope that the whole beam steering is going to be integrated either in a hybrid way or in a single chip solution.
Okay. I have to say that we have quite a few speakers and also companies in the room that are actually working specifically on the different type of the solid state beam steering. And I think one of them I can give spontaneously a word. That's Renato Martins from Flatlight. Renato, I see that you're there. Tell us a couple of words what Flatlight does.
Yeah, thank you, Olga, for the introduction. Yes, so in Flatlight, we're developing active metasurfaces, and we are aiming applications in LiDAR. So basically, what we're developing is ultra-fast scanning system that provides high field of view and can be integratable, and we can talk about later, Echo, if you're interested.
And I think, Renato, you're yourself interested in someone providing a high quality MEMS, right? Because you're working on the deposit, on really doing the meta surfaces, but someone needs to do the MEMS underneath. So maybe they're also partners for you in the room.
Yes, of course. If there's someone that, I can open to talk, and you can reach me out. I can put my email in the talk also.
Absolutely. Meanwhile, we have a couple of questions. So Heiko, for you, there was actually a very practical question from I lost it. Someone was asking about the resolution and the scanning speed of your long-range LiDAR. From the from the Aristotle University, Remis. Are you in the room, Reminis? If you are, please unmute yourself. Ronis Maximilianis, unmute yourself and ask your question. Silence. Okay, then I'll read it out. What is the resolution and the scanning speed of your long-range LiDAR, Aiko?
The resolution is around 0.05 degrees, so that's 20 pixel per degree. When we scan a narrow field, when we scan a wider field of view, we stretch the resolution, or we have non-uniform resolution. That's also possible because of the MEMS mirrors. It's pretty configurable, and the MEMS mirrors, they run at a kilohertz, around a kilohertz, a little above that, and they built the frame in a way that we achieve 10 frames a second. I hope that answers the question.
I think so. So there's also a question about this practical question from Edwin Evers. Edwin, if you're in the room, please unmute yourself, switch on the camera and ask the question. Edwin? All right, then I will go for it. Please define short, midway, and long range.
Hey, Evan. Excellent question. So short range would be anything up to 30 or 50 meter, depending on the application, and then mid range would be anything from the short range 20 to 50 to 100 meter approximately, or maybe 120 meter. Long range would usually be beyond 200 meter.
So this is right. This is the rule of that you need how many seconds to make a decision? Was 10 seconds, right? That's why you need this distance of 200 meters. I think the justification is something like this, right?
If you drive, so yeah, the range comes from the use cases usually. Mm-hmm. One of the very prominent use cases for automotive LiDAR is a lost cargo scenario where something small and difficult to detect lies on the road, usually some debris. And imagine you approach this in an automatic mode at 130 kph. You can calculate back from your braking profile, from the reaction time of the brakes, from the delay of your compute, when you need to detect this object. And usually you come up with a range that is 130, 140, 150 meters, and then you might want to track the object for some time. That also adds another delay. So that's why these long ranges. That's why we come up with such long ranges.
Thank you. We have actually another question from Matthew Weed. Matthew, are you in the room? If you are, please unmute yourself and ask your question. Yes, you're muted yourself. Welcome. Please ask your question. Introduce yourself. Where are you and what are you doing? And please ask your question.
Yeah, sure. Well, hey, everybody. Matt Weed from Luminar Technologies, one of the ones in that middle.
Oh. Damn it. All right, let's wait until maybe Matt. No. All right, then hopefully Matt will come back in the moment. Meanwhile, the question. What are your thoughts on the 900 community going back to from backwards from silicon PMs to SPADs? Purely ease of shoving more pixels into the box or something more? Heiko?
Yeah, I guess it's about resolution mainly, yeah, and about the digital nature of the return. Yeah, the digital signal is easy to acquire, and you get a nice high resolution. There's some marketing to it, I guess. Yeah, like with digital cameras, where people, like years ago, people would brag about their camera resolution. Hey, I have an 8 megapixel camera. Hey, I have a 12 megapixel. I have 24 megapixels, and so on and so on. There is marketing to this as well.
Mm-hmm. And we have also a question from Fraunhofer, from Matt Warden. Matt, if you're here, please unmute yourself and ask your question.
Okay, thank you. Hi. So yeah, another one about the requirements. Matt Warden from Fraunhofer Centre for Applied Photonics in the UK. So would you see the requirements and use cases like the ones you mentioned earlier changing in future, or is it already a pretty good consensus about what LiDARs need to be able to do?
I think they settled. They settled quite well on what we see today. So there was a lot of uncertainty 5, 6, 7 years ago, and requirements were changing day by day. But meanwhile, they are more settled as people learned to work with LiDAR, as people experienced the data, as people, as developers build detection models and detection models around it. They kind of figured out what really the requirements are they need. So I think the sort of requirements we have today, we can stick to them for the next years to come. Not forever, of course, right? With every next generation of LiDAR sensors, these sensors will evolve, and they will evolve in different dimensions. They will evolve in cost. They will evolve in pure sensor packaging volume, but they also will evolve in performance. Yeah, and once you gain more performance, you are not going to give it up again.
Matthew, are you back with us from Luminar, Matt? Yes.
Yeah, hopefully. My computer just crashed.
Did you have the answer for your question?
Unfortunately, I missed it, but I can catch up later. I don't want to keep the whole group for my IT issues.
But how is it going with Luminar?
Oh, things are going well.
I think you need to talk at the next meeting.
I saw this come up and I was like, wow, I guess we're out of touch with Optica somehow.
A little bit. A little bit, but actually, it's good that both of you in the room, because I would like to introduce one of the next speakers, who is the excellent provider for the state scanning systems, and that's Apurva Jan from Lumotive. Apurva, are you with us,
Yes,
please?
I'm here, and it's really good to see all these friendly faces. Very good to see you all, and
And
good to
all
see
these
you,
friendly
Matt,
faces are very
Michael.
much looking
Yeah,
forward to hear from you. So maybe start sharing your presentation and tell us
right.
what's new with you and what are you working on.
Absolutely, absolutely. I think I have a very short time slot here, so I'll try to stay within that. So, yeah, Lumotive, we are an optical semiconductor company, and we're building the next era of programmable optics. Our technology is based on metasurfaces. Just, I was hearing Flatlight talk about it. Metasurfaces, we build reflective metasurfaces. And our first products are geared towards the LiDAR industry. So we're building these metasurface-based, what we call light control metasurface LCM chips for LiDAR industry to provide truly solid state beam steering. And the main, the benefits of using the solid state beam steering, a lot of people in this room know to make compact and reliable systems. But what it also enables is digital control of the beam. So the way we can build frames or scan the scene can be highly dynamic and be very much software controlled. So our technology of digital beam steering with no moving parts is based on CMOS and LCOS technology. These are mass, volume technologies to build these truly flat optical components. Now, as a semiconductor company, we also build reference designs to kind of enable the module makers to build systems based on our core technology of beam steering. And the approach we have taken in this regard is quite innovative in the sense that we've enabled an open platform for LiDAR designs. And we built some LiDAR reference design platforms that enable a very simple architecture, as simple as a camera with an all semiconductor approach with no moving parts, and enabling all of these software-defined capabilities through our API and the software stack that we provide, again, as an open source to go with it. And this platform is highly scalable. This platform can be developed and customized from all the way from near range applications, all of these different use cases that Heiko was talking about, from near range applications with very wide field of views up to 180 degrees in the scanning direction, to long range architectures that go beyond 200 meters, all with a similar architecture that's kind of laid out here. I won't go into the details of that, that enable a truly kind of a common platform to address all of these different use cases in a solid state architecture. And our architecture as a beam steering provider, we're open to actually it is compatible with all of these different, components or architectures that we hear about. It's, compatible with VCSELs for edge emitting lasers, indirect time of flight or direct time of flight approaches, various wavelengths. So our chip can be, fabricated at 9xx nanometers, like Matt was asking, or 1550 or 1310 nanometers. To go into these different architectures and applications. There are, of course, pros and cons of all of these different kind of choices and trade-offs in the LiDAR world that I'm not diving into today. I want to touch a little bit upon what else does solid state enable, because we hear about solid state so much, and it's mostly from the cost and reliability perspective, but it also enables some features that are truly unique to solid state beam steering. And one of the key software stacks that we are developing is for adaptive sensing. And this really enables like very different use cases for end applications. And I have a couple of use cases here which show, kind of show the enablement of virtual LiDARs from a single physical LiDAR. And these can be highly adaptive. And in one situation, we show, for example, a pedestrian, when it's detected, you can reallocate the resources because of the solid state beam steering nature to the regions where you actually need it, and you can get more information on the pedestrian in this case, for example. And this can be used in real time as an adaptive sensor, or these features can be used to customize your deployment or keep things calibrated over time. Another use case is very common, again, in the automotive use cases is retroreflectors, or even industrial use cases where there's retroreflectors in the scene. And using these type of like this kind of solid, the software-defined capability, we can detect saturated pixels in the scene, and solid like retroreflectors. In this case, this triangle are known to show blooming or to also have range walk errors. And we can turn on the auto exposure mode to kind of get rid of these blooming artifacts in the scene in real time without any motion artifact with our software-defined capability and building up the scene. So just wanted to keep it within the 1 to 2 minutes that was given and give a quick overview of what we're doing, what are the solutions we enable, and how we work with our with the industry with these open platforms and enable LiDAR makers, OEM, to kind of use our technology and take it to market, and kind of the end applications or software stack that enables. Am I within my time limit, Olga?
Yes, you are.
Great.
Thank you so much for respecting it. But Apurva, tell us, what is, for instance, what is something that when you come to such a meeting, which type of the partners or maybe that you are searching for here?
Absolutely, that's a great question. So, as a component provider, we are of course very excited to work with our direct customers who are module makers, or typically like LiDAR companies building different LiDAR architectures. But the approach we take is we also we enable these reference designs so that the end users, like the OEMs or the solution integrators in various markets, can adopt our reference design and start developing their software or perception stack as well. So we kind of do both the push and the pull. We work directly with the OEMs and the solution integrators to enable the next generation of the perception stacks or their applications and speed that up. And our direct customers are the tier ones or the module makers in the various industries to kind of adopt our technology and build the next generation of solid state LiDAR using it.
Do you now mostly look at the automotive, or do you also explore alternative
We're
fields?
actually very broad in the LiDAR world. We are looking at because we're an enabling solution for beam steering. We are working with industrial sector, smart infrastructure, automotive. There are some early engagements on the consumer side because this chip is really scalable and can go down to really small sizes as well. And in fact, as a semiconductor company, we're also working beyond LiDAR because this is a foundational optical component which has applications beyond LiDAR. So as a semiconductor company, we are actually quite broad out there and enabling solutions that are you can utilize dynamic optical components, right, and enable kind of flat optical systems going forward.
Thank you so much. We actually have a question for you from the Aristotle University, and I hope that this time Ronis will really unmute himself and ask his question. Ronis, you're very welcome in the room to join the discussion. Apparently, he's very shy. Well, then I will read it out. Is the scanning 1D, Apurva?
Yes. Go ahead.
Yes,
Hey.
we got Ronis. Ronis, welcome.
I had an issue with my microphone. Hi everyone. I saw that also on the slide that scanning is 1D, but how about the second dimension? Do you have solution for second dimension as well?
That's a great question. That's a great question. It allows me to plug in our next generation product as well. So the current product that we have for the LiDAR market is a 1D, and the way we use it in LiDAR architectures is to create a line beam that can be scanned in one dimension. So think of it as a paintbrush that you can scan left to right or top to down, depending on how you orient the chip. And you're reading out columns or rows, right, at a time from your 2D detector array. You can also use it as a beam steering in both TX and RX for 1D receiver chips, right? So you can do both, TX and RX beam steering. But these are one-dimensional beam steering chips, which provide a good trade-off between the resolution that you need and the frame rate. So you don't have to do the full raster, and you can get a pretty high frame rate in that approach. we are working on our next generation chip, which enables two-dimensional beam steering. And we see applications of the two-dimensional beam steering in LiDAR, but we also see that application in non-LiDAR applications like optical circuit switching and areas like that.
Thank you, Apurva. And we have actually another question from Edwin Evers, but now he explained why he never goes live because his microphone apparently not connected. How about losses? And I think this is something that will be very important also that Renato can address. And I see him raising the eyebrow. How about the losses for this
That's
thing?
right. That's a great question as well. We work a lot, over the past 8 years to minimize the losses through these systems. These are diffractive structures, so you know how the diffraction works. You have always coupling into the different orders, right? In light. So where we are today is we are at 50% efficiency, which is 50% of the light goes from, from an input beam to the direction. And with this type of efficiency, we are already beating the cost and kind of the range per dollar or the range per watt, right, from compared to other architectures like addressable pixels and such, just because of the beam steering and the resolution that we can provide. The roadmap and where we can take this technology, our target is to go up to 80% by next year. So we see that this technology and our approach can go to 80% efficiencies, but there'll still be losses. This is not a mirror. It's a digital beam steering that enables multiple different functionalities. To summarize, today we are about 50% heading towards 80% efficiency.
Okay, thank you so much. So 50 to 80% efficiency, what our LiDAR developers say. Heiko, Matt, how is the number?
Sounds very, very promising. So Apurva mentioned it. The cost, there's cost to beam steering, and there's cost to no beam steering. If I develop a full flash LiDAR system which uses one VCSEL diode to stay in this example, use one VCSEL diode per direction or per area of the field of view, I use a lot of VCSEL diodes, and these are not silicon. These are compound semiconductor materials. So they have a price tag to it. And if I can reduce the number of VCSELs by using a scanning technology where I only illuminate part of the field of view, either a line or a row or a patch, that brings down the cost of the relatively expensive component VCSEL diode by a lot. And all of this money that I save on the VCSEL diodes, I can spend on scanning technology, for example. On the other hand, it makes the whole image acquisition more complicated. So a simple scanning and a versatile scanning method is very appreciated.
Okay. Matt, any comment from your side?
I think getting 80% would be a big deal. I mean, what is it? Used to be like 50% or something. That's still only, what, 65% round trip efficiency, assuming you're doing some sort of pseudo or fully monostatic or pseudo monostatic, which is still, you're getting high 90s with a piece of metal or piece of glass spinning around. I think the big benefit there is size, right? Because you can package it a little bit more tightly, which is certainly a benefit. I know for 2D scanning, I think it's just too slow, right? But for 1D scanning, it's probably just fine, right? Doing an array, basically 90% of the LiDAR, particularly that coming out of China, is basically an array on a polygon, and it's pretty straightforward to just replace that with this kind of device. And it's interesting, it's compelling, especially if the aperture can be more of the device size, right? That's like the long-term roadmap for LiDAR is how much of your front-facing area of like physical area of the device is collection aperture. Right, in the however many decades long future, somehow we'll figure out how to capture that whole area, that whole integrated area as collection aperture. But in the meantime, it's usually a pretty small fraction. I think the stuff from Lumotive Lumotive probably gets us a little bit closer, but that loss is still kind of painful. So you're trying to overcome that loss with a little bit more aperture, which is compelling.
Yeah. Another way to overcome the losses of course, probably to crank up the power a little bit. And then in this respect, yes, I actually would like to introduce another speaker to this conversation who maybe knows really well how to crank up the power, but also decrease the noise, which will help us to increase the precision and actually stability of the entire system. Ori from OI Waves, I love the title of his presentation, the ridiculously no noise lasers. Ori, welcome to the conversation. Tell us a little bit more about what's your offer to the LiDAR world.
Yeah,
in terms of the laser sources.
Yeah, just looking at where we fit into the LiDAR world. I'll start with the history of OE waves and LiDAR, and which is hinted at in the small print at the bottom of the slide, and that OE waves provided LiDAR systems to GM and sold off a part of the company to General Motors for their automotive systems department. And we are therefore not directly working in the automotive space, but we are happy to support people in the automotive space. So what we do is ridiculously low noise lasers and noise analyzers, at least as far as it concerns the LiDAR community. And so when you're looking at the distance and velocity measurements using LiDAR, you're looking at a change, you're looking at a difference in frequency. You're looking at a frequency shift. And well, if the laser source has an inherent frequency shift in it, then frequency noise in it, then that adds noise to your measurement. And so what we provide are the ultra low noise lasers with line widths down to the millihertz region. Instantaneous line is down to the millihertz region, and so that gives you the lowest noise you can get anywhere for LiDAR applications. And then we also provide for people that are making competing technologies. We provide them with a phase noise measurement system, or a laser noise measurement system. You can measure the phase noise, the frequency noise, and the intensity noise of your lasers as you're developing them, or also as you go through the whole system. You can look at, well, how do my components, how does the whole system affect the noise of the laser? Where are we running into issues? So these low noise lasers are excellent for FMCW LiDAR, and the extremely low relative amplitude modulation is also important for that. We have a technique integrated into the laser that allows you to chirp the laser at megahertz bandwidth and get with extremely good linearity, both in terms of how the frequency shifts, but also the power doesn't change barely at all. We got minus 80 dB relative amplitude modulation during the whole sweep. And so, yeah, that narrow line width provides you with a long coherence range and, in the end, reduced errors in your measurements.
What are the wavelengths that you're working on, Ori?
We work anywhere from 370 nanometers out to 4,500 nanometers. The way we build our lasers is that we commercially source the diodes that go into them, and then we basically apply our whispering gallery mode technology to narrow down the line width down to the hertz level.
You do the electronics magic.
We do the electronics and the optical magic to take a off the shelf or a custom built laser diode and reduce the line width on the order of 10,000 fold, or we're reducing the noise by about 60 dB.
Can you also do the 1550? Because this was always the classical problem, because the 1550 good lasers are rather expensive, but then it's the eye-safe laser wavelength.
Oh, absolutely. Absolutely. Yes. 1550, we can go sub-hertz as shown on the graph here in the bottom left. These are our three models. In the in the C band, so at 1550. So the XLN laser here, as you can see, has a subhertz line width.
Thank you. Any comments? Matt, I know you're working on 1550. Does it look like something interesting to you?
I think we're sticking with pulses for now, but that looks like a really nice laser output.
Very good. And I would
If you ever run into noise being an issue, you should try one of our lasers and at least see if the laser is the source.
Yeah. Oh, yeah. There's definitely in the wrong LiDAR architecture, noise is definitely a problem. Yeah, agreed.
Well, I will make sure that you two are in touch after the meeting. I think there might be a room for a conversation there. Meanwhile, I would like to introduce actually our next main speaker, for whom a precision is of high importance. So, Ori, it's something also you potentially should work with, because precision becomes very critical when we speak of the very low or short distances, and that's where we speak about vision. And I would like to, with this, I would like to switch to our next end user and system integrator presentation, Anand Govalan from Vayu Robotics. Anand, tell us, how is it a go or no go or maybe for the LiDAR for the vision? The floor and the attention is all yours.
Thank you. And good afternoon, good morning, everyone. Thank you for inviting me to the presentation. Let me first pull up my slides and make sure that you can see them.
Works
Are
perfect.
you able to see my slides? Perfect, great.
Absolutely.
So I'm going to spend a few minutes with this sort of slightly provocative headline, which is LiDAR even needed for robotics? And by way of introduction, for those who don't know me, I'm an old LiDAR guy. I was the CTO and the CEO of a company called Velodyne LiDAR, and I took the company public in late 2020. And little did I know that I started the whole public LiDAR wave. And now there's a lot of friends in this room who are part of companies like that. And then after running Velodyne for about a year after it went public, I then decided to go back to the ground floor and rethink all my assumptions, and went from becoming a LiDAR guy to becoming a robotic systems guy. And so today I'm not going to be wearing my LiDAR hat. I'm actually going to take that off and I'm going to put on my robotic system hat. And so at Vayu Robotics, we started the company really to rethink software and hardware architectures for mobile robots, having basically sold LiDAR into all the major autonomous vehicle projects of the day. I realized that people were building systems that were far too expensive and not scalable. And so we decided we're going to think about this from the ground floor. And we put together a really interesting group of people. My two co-founders came out of the Apple self-driving program. And of course, everyone knows Dr. Jeff Hinton these days, who's a very well-known AI and machine learning engineer who's an advisor in the company. And so I'll first show you one of the products that we built, and then I will then use that to talk about what we see are the needs in the robotics world and how robotics as an application has evolved from a sensor need perspective. So what we built was a mobile delivery robot that drives at 20 miles per hour on outdoor environments, carries about 100 pounds of payload, and can be built for $5,000, right? So you will see here in this video effectively a grocery delivery application where a customer goes and orders groceries. The robot runs a modern AI stack, so it can essentially follow the packer inside the grocery store. And you can see a sensor package on that robot that does not include LiDAR. And so this is let's call it a Vision Plus robotic system, capable of functioning in daytime, nighttime, and a variety of different weather conditions, and is able to do fairly precise lateral localization without using LiDAR, and then delivers goods and then moves on. This is now currently functional and we are doing real-world deliveries in a couple of cities in North America. So this is kind of what is possible, and this is what we have built as our first product. And I think if you kind of take a step back and think about the world today, I think there's obviously we are at a very interesting point in the world of robotics. There's people like Elon and Vinod Khosla who have said there's going to be 1 billion robots in the next 20 years. Maybe this is, I don't know if this is true, but certainly we are seeing a lot of robots out there, and the number of robotic systems is growing across a variety of different form factors and applications, whether it's humanoids, whether it's tractors, whether it's warehouse robots, and so on and so forth. And all these robots need eyes. So clearly, sensing continues to be a very, very important problem to be solved for robotics. But the requirements for sensing in robotics have changed and evolved a lot, even in the last 5 years. So most people in this room, including myself, spent a lot, maybe the last decade of my career working on systems like what you see in the screen in front of you, right? So the idea is you have multiple sensing modalities. You have cameras, LiDAR, radars, ultrasonics. They all provide information into either an early fusion or a late fusion stack. You have object detection, segmentation, localization, all these software modules that do these different tasks. Then you track dynamic objects, then you do prediction, behavior planning, and then you essentially provide a control output to a robot. This is how robotics software has been built for the past 20, 25, 30 years, right? This works very well. There's a lot of companies and a lot of successful businesses around this, but there's always been a fundamental challenge that we have all grappled with, right? The hardware is always inevitably too expensive, and the software is inevitably very brittle, which means you have to write bespoke software for every single application, and the hardware set is always an order of magnitude more than you wish it would be. And that has been the trend for robotics for a very long time, and until the last 5 years. And I think you are now firmly in this world of robotics 2.0, where you have gone from this series of software modules that do all these different functions into a single AI model. And just to tell you that this is not just a research project, that robot that I showed you the video of runs exactly a stack like this. So it's a single neural network that goes from sensor input to output. And so the holy grail, of course, is if you can somehow take this magical neural network and combine it with low-cost sensors, you can effectively provide a robotic system. The reality of it is there are a lot of challenges to make this happen. From a software perspective, having data scarcity is a big challenge. Like, you can't scrape the internet like you could do with a large language model. So how do you create data sets that can actually be used to train AI models? And then how do you make that run real time on low cost compute? But then also, most importantly, for this group, these are still need to be safety certified and safety critical systems. And this is where the real challenge comes for sensors. I think everyone understands that vision can become a primary sensing modality and can effectively make these systems incredibly powerful and intelligent. But the question is vision sufficient to provide the safety guardrails for a robotic system? And that thinking is still evolving. I think there is, I would say very strongly that I believe vision is going to be the primary sensing modality to enable most of the functionality of the robot. However, vision has its known challenges with respect to being safety certified and providing safety guardrails. And I think this is where there's going to be a lot of interesting work in the near future. So from a LiDAR perspective, what does that mean? So I put together this chart, and I intentionally said yesterday and tomorrow, because as we heard in the previous discussions already, that today is dynamic and changing very rapidly. What today is in flux significantly. But if you thought about LiDAR, I'm going to call it tomorrow, which maybe for me tomorrow is when I was in Valladine. And so that my information is already 3 years outdated. We were talking about LiDAR systems that cost a few $1,000s. that had many different complex architectures, and maybe this is still true today to some extent, but that is changing. And for robotics specifically, LiDAR was used for sensing and avoiding, for localization, for generating HD maps that the robots could localize on. And there was always this early fusion, late fusion debate, which maybe still exists in the automotive world. It's also existed in the robotics world. And then there were always bespoke software pipelines, right? So you had a LiDAR pipeline, LiDAR processing pipeline. I'm sure there are companies in this group who provide LiDAR software as well. And this was the world, in my mind, that was the world of yesterday for robotics. The world of tomorrow, I think, is LiDAR systems that are significantly lower cost. So effectively, that costs less than $300. If you asked me a year ago or even a couple of years ago, I may have said $500, but that number is rapidly dropping. Keep in mind that that entire mobile robot that I showed you has a bill of material cost of less than $5,000. And so that's really what you're competing against, which that naturally means simple manufacturable architectures. Right? We all know the classical trade-off between performance and manufacturability for LiDAR. And in this case, your LiDAR system has to be manufacturable at scale to be able to bring the cost down. I believe LiDAR will be used, and this is, of course, my opinion at this point, will be used for safety guarantees. And that's going to be the primary strength that LiDAR brings to the table, because you can get very precise depth measurements that are physics-based and do not rely on machine learning or any derivation of information. And then also will be used to figure out where you are in the world when you don't have GPS. And I think LiDAR still continues to be the best modality to provide precise depth measurements, which can be used with traditional SLAM architectures. The output data requirements in the software pipelines have changed dramatically, where I think more and more you will see the need for data to essentially be in a form that can be consumed by standard neural network architectures, including transformer-based approaches, and it needs to feed into a standard ML pipeline. And so I think that for LiDAR to be useful for the robotics of the future, these are the sorts of things that will become relevant as we transition to this new world. At the risk of being too provocative with this group, I will ask the question, can vision go all the way? And I'll show you an example of what I think is state of the art in robotic vision. And this is a sensing modality that we developed. And basically, this is a planoptic camera, but built at very low cost. So what that means is it's sensing not just average intensity, it's sensing polarization, it's sensing other aspects of the photon, and then fusing that together using computational imaging and machine learning. As you can see, you can get RGB on the top left, but you can also get fairly high resolution depth. You can even get occupancy like surface normals, material property detection, where we can detect black tires and fallen debris. We can detect surface textures. So all of this other information without active illumination. So no lasers involved at all. And so this, I think, is state of the art for robotic vision. And these are the sorts of vision systems, if you will, or vision plus systems that robots are starting to use today and will use a lot more of in the future. So then the obvious question is, what can LiDAR help with? And here are the things, and this is not a complete list, but here are the things that I can think of. I think ultra low light continues to, of course, be a challenge. So in applications where you're talking about sub 0.1 lux illumination, definitely there's no other solution that works. I think localization in GPS denied environments, as I mentioned before, is an area where, again, LiDAR shines. You can use a visual inertial odometry based system, but it doesn't ever have the precision that a LiDAR based odometry system has. Mapping and inspection in unstructured environments continues to be a very robust industrial application where, again, a LiDAR is naturally suited to create three-dimensional twins. Safety guarantees is an area where LiDAR is going to be very useful and important. because all of these robotic systems, as they move around in the real world, will need safety guarantees and guardrails. And last but not the least, I think there has always been this promise of velocity. And velocity, as we have explored neural network pipelines and the inputs, turns out velocity is a very interesting and powerful input for vision transformers. And so I do think velocity could be a very interesting input that can really help robots do a lot better, but with the following caveats. So ultra low light cannot be used in defense applications. No defense autonomous system will ever accept active illumination at this point. So defense systems are moving rapidly to passive sensing. When you talk about localization, it still does have to fuse with modern low-cost RTK and visual inertial odometry. So rather than LiDAR becoming this high-resolution, expensive device that's used for localization, we see a world where there's a lower cost LiDAR that's fused with other odometry systems that provides enough robustness for the overall odometry solution. And so I do think that that's the way we should start thinking about even the problem of localization and odometry. When you're talking about mapping and inspection, the challenge is going to be to do it with significantly lower cost without loss in precision, right? So we are seeing the large airborne LiDAR systems like the Leicas, which used to cost $500,000, now going to $50,000, $60,000. And so even for very expensive mapping applications, you are seeing significant reduction in cost as technologies evolve. When you're talking about safety guarantees, I think for any LiDAR provider who wants to work in robotics, SIL certification is a must. So you have to be safety certified and do all the hard work to essentially be able to do that. In my mind, this takes away the ability to use a lot of beam steering approaches that are not rugged and reliable and robust. And so there's definitely, there's a smaller set of technologies that will be usable. And then, and last but not the least, as I said, low-cost velocity is really interesting if you can do this at low power as well, right? And one of the challenges with traditional FMCW has always been that the power budget just explodes. And we still are talking about systems that have to ultimately come in under 15 to 20 watts on a robot, because my entire robot has a 3 kilowatt hour battery. And so those are the sorts of interesting solutions that we are looking for in the world of robotics. So in summary, I think software architectures have evolved significantly for robots, and there is a huge opportunity. We do believe that robots will be like as big as the next smartphone in the next 20, 25 years. Hopefully, each one of us will have our own personal robot 20 years from now. Cameras and vision systems have become the dominant sensing modality due to the advent of vision transformers. So in a sense, I hate to admit it, but Elon was sort of right, or half right, if you will. But LiDARs do have a role to play, I believe, in safety critical usage and applications, but they will really have to find the right trade-off between manufacturability and usability to essentially drive adoption.
Thank you, Anand.
Thank you for your attention.
Thank you so much, but I have to say that I already have my personal robot. It's called Robbie. It sits underneath my couch and does the vacuum cleaning for me. Thank you so much. And we actually have, I'll start because the first person could not anymore control the emotions. I said that remarkable technology. Congratulations on this one. And we have actually quite a few questions. And one of them is coming from Mirvey from the Scrumblocks. Mirvey, so up to you, please unmute yourself. What's your question?
Hi, Anand. Thank you very much for a very nice presentation. You said that it's bespoke software stacks are required. However, as you're aware, ROS and ROS2 are taking over the world right now, which means it allows both for you to control the specs while you're doing sensor fusion and you're doing perception, building your perception stack. Now, let me be very frank, not the whole world lives in California. I actually live in the Netherlands. And for me, most of the time, the cameras are not really useful because of the rain and the fog. What's your feeling? What's your thought about having maybe a region-based or a need-based feature in a ROS-based type architecture? What do you think about that?
Yeah, first on the ROS2 point, yeah, I think ROS2 are a great sort of base middleware layer for a lot of, let's call it low volume applications. The moment you get to higher volume, almost everybody moves away from ROS because the safety and timing guarantees that you need for the robots require ultimately some time critical middleware layers. And what that means naturally is the moment you do that, then the LiDAR or any sensor sort of software pipeline starts becoming somewhat bespoke. I think there are efforts to standardization there, but today, as it stands today, there is no one standard off-the-shelf solution we can use. The ROS2 works great until you get to a certain level of maturity. So I think that's the thing that we see. In terms of weather, I think that's a great point, and I didn't spend too much time talking about it. Even some of these passive sensing systems that I described today can actually do interesting things with weather, because it turns out that you can actually do things like remove, defog a scene effectively, and we can show that even with our own passive sensor, because the polarization states of light which are scattered by fog are different than the targets that are not scattered by fog. So I think that, and then when you have very, very dense particulates, LiDAR is pretty much useless anyways also. Only radar is the only sensing modality that works in that situation. And so I think you will see, yes, weather is an important one where vision systems actually are capable of working well now in some of the, let's call it moderate weather situations. And if you have very, very harsh weather, then I think the challenge is across the board for any light-based sensing modality.
I think we're going to have also later in the meeting a comment from Zach Boniface from John Deere, also about the weather and everything that comes with it. Meanwhile, we'll also have another question from Celine Development, Jan Wolhead. Jan, if you're here, please unmute yourself and ask your questions.
Hi, I hope you can hear me okay.
Yes, we hear you perfectly.
Yes, we can.
The question I have is related to what optical specifications on a robotic system would you be requiring as a robotic system manufacturer or designer?
Yeah, so it sort of depends on, usually what we're seeing is you're seeing two modes of operation. So I'm intentionally sort of excluding any system that moves faster than 20 miles per hour, because I almost think that's classified as a vehicle, not a robot, but that's a semantic point. So generally, you see two regimes of operation. One is mobility, which is moving in the range of between 0 to, let's say, 20 miles per hour. And then you see much shorter range, low speed, but high precision applications. So you're thinking about grasping something, picking something up, and so on. And today, many robotic systems have almost two independent sensing systems that somehow fuse in the middle to solve those problems. I think eventually there can be one system that solves it, but that drives the optical specifications of the system. So with that in mind, so what does that mean? What that means is for most robotic systems, you're not looking at very long range. So you're looking at much more contained focal lengths for the system. But you're looking at very high precision, especially for pick and place. And not only precision in the order of going to sub 1 centimeter type of precision for the ability to estimate depth and to estimate pose. These are the sorts of things that would drive sort of the optical specification for the system. Resolution becomes less critical, but it is important, right? Like you do want, let's call it 1024 by 1024 sort of resolution in a 120-degree field of view. That's the sort of resolution requirements that we see.
Thank you. And we
Yeah.
actually, I wanted to introduce to you to the OMITedia LiDAR, who does also technology specifically for 3D sensing. I believe you probably have heard of one another, so I think it might be interesting to see what they are capable of doing. Jose, please tell us a couple of words of what you do and also show what you can
Can I
see
sit here? I have
with
a
your
short meeting.
systems.
Yeah, thanks a lot for the introduction, Olga. Let me share my slide. So, yeah, my name is José Luis Rubio. I am a VP and one of the founders of OMITedia. And sorry about this. Yeah. And what we do at OMITedia, we develop FMCW LiDAR systems and sensors. So what's different about us is that we do this in a massively parallel way. So what you see here on the left is our first line of products. It's called the Q series. We developed the Q1 a few years ago, and this here is the Q2, which we presented last week actually. And these systems are actually intended for high precision metrology of large structures, so it's more for like industrial applications. You can see also the side now is not really something you would still like to put on your robot. And the fact is that since we do FMCW LiDAR, we can measure both distance and speed within the field of this high precision metrology gives information about the vibration of structures. So we are using this mainly for applications in aerospace, for instance. This here on the left is a very large reflector, which is 14-meter wide. The accuracy we can get here is really high. It's in the range of 0.1, 0.2 millimeters at these long distances. And we also have applications in manufacturing, like in car part manufacturing, here on the bottom. And that's for the metrology part, let's say for the shape of the construction part. And for the vibration, we are also seeing many uses in dynamic analysis of structures. So here you see a plane, actually, an old plane. And this image on the right is the blue and red image is one of the vibration modes of the wing of the plane, actually. So this gives a lot of information to structural engineers. Also for civil engineering, this is a bridge of the high-speed rail in Spain, in the south of Spain. We have some units which are monitoring the vibrations of the bridge when the train passes by. So here on the top you see velocity signals when the train passes, and we can also integrate and get the displacement signals, very small displacement. So the range here is plus 0.5 and minus 1.5 millimeter. And we are measuring this at long distances from, in this case, from 10 to 30 meters more or less. And we can, of course, combine both things, metrology, dimensional metrology and vibration. And this on the bottom, this is an example. This is the engine of a car, and we can reconstruct the shape and then also turn on the car and reconstruct the vibration frequencies of different elements. So this is what we have now, our commercial product line. Beyond that, we have a development line, which is the ANT sensor, which is here on the right. And this is a sensor which is more engineered with the requirements of mobility and navigation applications in mind. And here also our intention is to commercialize the sensor, development kits to build that to integrate that into a larger system rather than the full system, which is what we do in the metrology market. So this system will be based on, the ANT sensor will be based on the same technology. It will have 1024 sorry, parallel channels. It's also based on FMCW, so it can measure distance and speed. And yeah, and as I said, we'll have different versions, and yeah, we believe it can be very useful for applications in.
What is the range of your system, Jose? Is it good really for vision, or what? How far away ahead can you look?
So if I briefly refer to the current ones, the Q series, the range is standard range is up to 50 meters. And for the AND series, we will have different variants. So initially, the first ones will go like from 20 to 50 meters, and which is, we believe it's adequate for many robotic and mobility applications. And we, of course, have other developments down the road aiming at 200, 300 meters for automotive, but that's beyond this. That's not so. This will be in a few years.
Okay, we actually have a question to you specifically from Vayo Robotics. Please, unmute yourself and ask your questions. But Anand, are you also playing on the terms of the Vayo? Yeah, go ahead.
Yeah, I mean, I think, as I said before, velocity is a very interesting parameter for any robotic system, especially if you're moving. And so I was curious about the field of view and the power consumption of the ant sensor.
Yeah, I can, if you are interested, we can send you the data set for this. So for the field of view, we have several options ranging, if my mind doesn't mistake me, from 50 to 90 degrees. And for the power consumption, I need to get back to you, but I mean, it's definitely not in the range of things that were worrying you. So the laser powers we are using are in the hundreds of milliwatts, and the full power system, I mean, full module power consumption in the range of 10, 20 watts. It depends what you include. So this what you see here is the full transceiver. So all the optical part, and the connector is a digital connector. This sends the data to an FPGA, which is where you gives you an IP with the signal processing. So if you take that into consideration, also the power is a bit more.
Thank you for the comments.
Look forward to an offline discussion. So
yes, I'll connect you too. We actually have a question from Matt. Matt from Luminar. You had an interesting question about AI hallucinations. I guess it can be applied both and to Vayo Robotics and also to Matidia. Matt, what are your thoughts?
Yeah. So it's really a thought from the approach of just throwing everything into one of these big end-to-end models. At the end of the day, like, they're making good progress, but there will always be some long tail of literally random probabilistic, what they call hallucinations. And so, for example, like Wave and some others who are looking at similar approaches basically explicitly say we want to have a totally non-AI pipeline, which kind of has to be LiDAR to be able to be reliable, that says you can drive here, you can't drive there. If your AI system proposes you to swerve out of the lane into something and there's nothing there, don't do it, right? These kinds of things. So I was just curious, it sounded like your approach is to continue to put everything into the foundational model and hope that it just pushes those hallucinations to a small enough number that it's palatable.
No, I think you do need a parallel safety system that's end-to-end based, because there is always a probability of a hallucination no matter what you do. So that's what I meant when I said there is safety guardrail, right? So in our robots also, we have a safety system that is purely physics-based. But even there, we have to be careful when we say that LiDAR is the only solution, because you can have stereo camera-based depth, right? That can work very well if you can do away with all of the inadequacies of a stereo camera, which is in sparse features, basically stereo depth fails, and low light stereo depth fails, and so on. And so what we have done with our light field or panoptic sensing approach is to do away with some of those inadequacies of traditional stereo cameras. So we can create a depth pipeline that is purely non-ML based, right? It's semi-global matching based, but it's far more robust than you would get with a traditional camera, right? So having said that, I do think LiDAR is a powerful thing to have in your safety system. My only point there is that you can't now justify the presence of an ultra-high resolution, ultra-high cost LiDAR. Your safety system would have to could use a combination of some, let's call it moderate performance, low-cost LiDAR in combination with stereo depth. And that is probably sufficient if you just want to prevent bad things from happening.
Thank you. Jose, and how about you? Do you also develop the processing software yourself for your sensor?
Yes, that's right. We do actually for the Q series we had to develop the full system. No? So we designed the photonic chip, and we built the electronics. Of course, the electronics are a combination of off-the-shelf and custom electronics, and with that we built the full system and all the processing chain. So now we are also applying that to the ANT series, and with the addition of custom ASICs in this case, which are required because of the high data rate, which we don't have in the case of the Q series. No, Q series is more slow and precise measurements. So yeah, it's an important part of the performance of a LiDAR system. The right signal processing is, we think, is key. So we like to do that ourselves.
Indeed. And I think also one important part of the proper LiDAR development is also testing. So this is why I would like to introduce to the floor our next speaker, Mirvay from Scramblux, talking about the testing of the actually functional testing of the entire LiDAR systems, which I believe will be highly beneficial for all the LiDAR manufacturers in the room.
Thank you very much. Elisa, can you help me, please, with the slide? I will just wait for the slide. Hi. As they say, now to something completely different. Yeah. So I'm going to tell you about, could you put it on full screen, please? Is that possible? Yes. So I'm the CTO of Scramblux. Scramblux is a German company. And we have built an instrument for end-of-line testing of LiDARs. So, I mean, one of the key issues today has been, of course, the cost of the LiDAR. And a lot of the cost generates usually from the fact that the factories are very expensive. One of the key things that is holding up the cost is actually the end-of-line testing, where you need huge tunnels, 30 to 50 meter. And 50-meter factory space is very expensive. So we have built a tiny, I would say, about 1.2 by 1.2 meter LiDAR tester that generates basically a 3D checkered board, as you can see. This is very similar to if you think about in the cameras where you have a 2D checkered board to calibrate your camera. In this case, we have built a 3D checkered board where we scan a 3D pattern across the field of your LiDAR. We have also developed our own target based on optical lithography, which can be used for identifying the resolution of your LiDAR. So hopefully we will try to work towards that $200 low-cost LiDAR. Now, having said this, what we have built is a complete, as I said, it's a concept, and the concept we're hoping to follow the LiDAR throughout its lifetime, all the way from tier ones to OEMs to, especially in the automotive business, to the PTIs for the inspection afterwards. This is to help both the lean process of continuously developing your product, improving your CIP, but simultaneously also to follow the LiDAR through the life cycle with a single metric. And that's the key here, because at the moment, there are so many metrics, so many different devices. It's not possible for example, an OEM to compare various devices against each other. Our one key thing I should mention is our instrument is completely agnostic to the type of LiDAR, except flash. We can't do flash, only scanning beam LiDARs. So it's completely agnostic in that sense, time of flight, FMCW, whatever. I mean, whatever you can come up with, as long as it has a scanning beam laser, can be VCSEL, can be edge emitter, doesn't really matter to us. And importantly for now, we have the prototype ready. We are open to testing for you. If you have testing needs, contact us. We will test this for you in an instrument to show you what it can do. Today, the instrument is focused on the 905 nanometer. We are hoping when it comes into the field to cut down the cycle time significantly for a LiDAR and hopefully then bring down those €200 LiDARs. $200, sorry, it's a bit less even. And what you see here is one thing, and that is how many targets you can have per frame. And that's something we can control also. We can go from one target up to 15 targets, and the targets are equidistant. We have an absolute measurement where we know with the 3mm accuracy where each target is. Then we also have a relative measurement where we know the period between the targets. And that's how we qualify the LiDAR. Essentially, we have those metrics from our instrument. We put your LiDARs in. We use very, very simple AI in this case, where we use a classifier to just identify our target. And from this, we can just tell you pass or fail, depending on how it goes. Lots of words, completely different topic, as I said. Very open to questions. Thank you.
Thank you so much, Mirve. So I've paid attention in all the LiDAR manufacturers, Continental, Vayu, Luminar, they were very consumed. So gentlemen, Zach, now it's your time to challenge Mirve and ask, okay, can you do this? Please, Anand, do you have a challenge?
I think the question with testing systems like this has always been the ability to test for range without effectively losing the light along the way, right? So how do you deal with range testing, and how do you deal with that without effectively, uncalibrated losses in the testing system itself?
So the key, good question, actually. It's a good, you can see the principle, I understand. So first of all, we use retroreflectors. We don't use Lambertian targets. And we have a model we have derived an analytical model for calibrating the retroreflector to Lambertian in free space. That allows us then to do these kind of calibrations in this environment. And I think you understand how the unit cell is working. That's one of the key that we have. The second reason that we can do this is, of course, we wait for customer requests. At this moment, as you saw, I have 35 meters because we took off the shell parts. But for somebody like Omatidia, we would use a different coatings on the mirrors, etc. This is all an issue which we leave up to the customer to put the price point where they want to put, and then we deliver the product. Good catch, by the way. I'm just going to mute while the question comes.
Thank you so much, Mirve. And with this, I would actually like to also give a floor to another solution provider. And if you look at the webpage of Exail and Nisifor, so they develop the systems for all the possible applications in LiDAR, in navigation, in space, in agriculture. So Nisifor, tell us about what are you using LiDARs for, and what is your solution for the field? Nisifor? We probably don't hear you. No, we don't hear you, unfortunately.
Is it better now, I guess?
Yes, much better now.
Yeah, so sorry for that. Yeah, so as you say, Excel is quite a large company, and we have kind of two things. We do systems, and another one is we do components, and I will focus more on this side, on the components we do for LiDAR, okay, and for high-end LiDAR based on fiber laser. So one, I will talk briefly about three components we have for that. One is top fiber for people making pulse amplifiers for LiDAR, and we cover all wavelength range from neodymium, erbium, ytterbium fibers, thulium fibers for 2 microns. And we have really optimized the matrix of these fibers for high peak power. For example, we have some fibers that are used in wind LiDAR measurements, and it can measure up to 16 kilometers the velocity of the wind with very high resolution. We also developed some patented matrix to increase the radiation resistance of this fiber. So our fiber could be used to make LiDAR for space, for example, for dock station of satellites. Another range of products that we developed are some modulators. And we mentioned, a few people mentioned frequency modulated continuous wave LiDAR before. So here we have some very good modulators with low VPI that are able to make some very fast frequency shift for this kind of purpose. And we are able here again to match a lot of different wavelengths. And the last kind of component we can provide if you're building some LiDAR is some micro optics assembly of kind of card, I would say, business card size. So it's not peak, it's still a bulk optic, but I would say some very compact bulk optics that can be used in very harsh environments in terms of vibration and shock. So if you need to have very high PR, if you want to make whatever coherent detection, or even some frequency doubling module, for example, if you want to go to visible light from infrared light. So these are things we can really tailor to your needs. So that was for my brief overview of the components we can provide for LiDAR manufacturers.
Thank you, Mr. For beauty is always in simplicity. And I think while people will think about the attendees will think about the questions, I would very be curious, because you've mentioned that the last one of your assemblies is also stable for alignment and especially in harsh environments.
Yes.
What can it survive?
Well, it can really survive to, for example, we have tested that for space mission to go on some launchers or on some satellites. So really in terms of shock and vibration, it's really robust.
I think because robustness is something of the main concerns for our next speaker, and it's the Zach Bonifaz from John Deere. John Deere is, famous for producing all the type of the machines for and constructions and agriculture, and I guess that is the definition of nearly the harshest environments. Zach, tell us what are your requirements and what are your interests in LiDAR, and most importantly, do you think it's a go, maybe, or no go?
Okay, well, hopefully we'll get to that. Olga, thank you for the opportunity to speak to this amazing collection of LiDAR expertise. So I presented in this forum a couple of years ago, I think it was, and obviously our perspectives on different sensing technologies evolved, but my message hasn't changed a whole lot. Let's see if I can advance this slide. So some of the application spaces that we work in, right, our machines work in a very diverse set of environments, but some of them lend themselves better to LiDAR than others. Orchards, for instance, we feel like that environment lends itself much better to LiDAR than some of the other sensor technologies that we use. But when we get out into broad acre farming scenarios, we see a lot of dust, an awful lot of dust, right? We're working the earth with most of our agricultural equipment, and also in construction, right? We have a very large construction business as well. Dust accumulates on the optics, and keeping LiDARs clean can be a real struggle. And the airborne dust gets really, really, really thick sometimes. Now, in our experience, not all LiDARs are anywhere near close to equal when it comes to dust penetration, but all of them has a physical limit. So my advice is to be as good as possible as the physics will allow. And we're certainly interested in seeing how far we can push 1550 nanometer LiDAR in terms of dust penetration. I want to be a little bit frank here, with the advancements in radar and the resolution there. We're getting closer, I would say, to LiDAR-like performance with really good dust penetration. In terms of ruggedness, Olga, you're exactly correct. We have very, very high standards. We tend to see higher vibration on our equipment, more shock than you would typically see in an automotive environment. Our electronics oftentimes need to be resistant to more chemicals than you would see in an automotive scenario. And then we also expect our sensors to see some impact. Tree branches, for instance, are something that are quite common to strike our sensors. Wide field of view, this is because our equipment tends to turn very sharply, okay? So either the LiDAR sensor needs to have a very wide field of view, which is difficult to accomplish with a solid state device, or it needs to be inexpensive enough that we can distribute them around the vehicle as we need to, and then also time synchronize them. Many people probably don't know that John Deere is also vertically integrated from a GPS perspective. We develop our own GPS sensors and maintain our own global RTK network. But we're increasingly interested in fusing perception with GPS in GNSS, either denied or degraded environments. And certainly we think LiDAR has a lot of promise there. So we're really interested in FMCW and coherent LiDAR and what that can do for us. And then also we find that a lot of these odometry techniques work a lot better when there's an IMU integrated directly into the sensor. Doesn't need to be a really expensive one. Even a fairly cheap IMU goes a long way to improving whatever kind of odometry you're attempting to do with the sensor. Going back to the dust penetration, we've actually done quite a bit of testing of different sensors and done some elaborate tests to look at how well different sensors can penetrate dust. And right now we even have actually this dust chamber in Fargo, North Dakota is fully commissioned now. So if you have a device that you think would benefit from some dust chamber testing, maybe we can talk and get you into that facility in North Dakota. Interestingly enough, there's not too many people demanding to use the chamber in January in Fargo, North Dakota. So if you're interested in going to Fargo in January, I bet we can squeeze you in. Anyway, that was my last slide.
Thank you, Zach. I think Merva is already laughing about the January. What do you in terms of you when you speak about the basic parameters, range and field of view, what would you say is sufficient for your applications? What are you looking at? Is it as the same for the automotive beyond 200 meters? What are the angles? Do you want to see 120 to see if the tire flies somewhere? Or is it just that it's unbreakable?
Yeah, certainly we don't have the same range requirements as automotive. There are scenarios where we want to see out to 100 meters, but I would say the vast majority of the time our sensing is within 50 meters.
We have a very funny question from Heiko. Heiko, please unmute yourself and ask.
Zach, hey, I was very interested about your dust test chamber, not so much about the comment about testing in January in North Dakota. We see a lot of different dust particle sizes, right? And also different LiDAR systems would be affected by different particle sizes. 1550 nanometer versus 900 nanometer. The backscattering would be very different with the same sort of particle sizes. So what's the range of particles you are testing in this facility?
That's a really good question, Heiko. We are restricted to dust particles that are non-combustible, as this chamber is contained indoors, right? But I think any sort of commercially available dust, right, that is not combustible is what we could use in that chamber.
We also have a further question from Merve. Merve, you had when you stopped laughing, please unmute yourself and ask the question.
Yeah, sorry, I was also taken by the comments on Dakota. No, I have a different question actually for agriculture in general to Zach, because one of the key things I would expect you guys do a lot is sensor fusion with different imaging sensors. So for example, let's say thermal cameras, but hyperspectral imaging fused with LiDAR, for example, so you would have an RGB plus, a point cloud plus hyperspectral data. Would that be something that is interesting for you guys?
Yeah, certainly we're not doing a ton of sensor fusion right now, to be honest, but it's certainly an area of research for us, and certainly hyperspectral imaging and multispectral imaging is also an area of interest, just due to being able to sense beyond the visible spectrum can often tell you a lot about the health of a plant and things of that nature. So yes, we do quite a bit of that. The challenge comes a little bit at night, right? Because our equipment operates during the day and night, and now you need to illuminate beyond the visible spectrum at night, and obviously our working lights that are integrated into our machines don't currently do that. But I would say operating at night in general is just, especially with any optical sensor, very challenging. Even with cameras, just due to the backscattering of light from our working lights. Our working lights are extremely powerful, and they need to be in order to have 360-degree visibility around our equipment.
And there is also specific question from Nicephore from Excel. Nicephore, please.
Yeah, I wanted to know that regarding dust, is there any better wavelength than another for the LiDAR?
I'm sorry, any better wavelength?
Yes, yeah.
Yeah, I mean, in general, right, we find that the longer the wavelength, the better. And also another thing that's attractive from our perspective about 1550 is somebody else earlier mentioned eye safety considerations. And also you can just go higher power at that wavelength. We're not as constrained by the need for low power, I would say, than other applications.
Thank you. I have a question for Jose. Jose, so how do you think frequency modulated CW at 1550 specifically for ZAX application? Is it possible?
That's a good question. We will be really looking forward to do some tests. I don't have data on that. So,
well, I'll give you some time. I would like to remind everyone that if you would like to be connected with some of the speakers after the meeting, please let me know. I will be happy to facilitate the connection. And meanwhile, I'll smoothly move to our last two presentations. I'm really apologize that we run over time, but I think the discussion is so exciting. I think all of you so much for contributing, so bear with me. And I would like to introduce actually one of the entities that is probably able to develop anything for anyone. And this is IMEC and Marcus Dalle. Marcus, tell us what will be yours, like touch on what you can do for the newest LiDAR developments.
Thank you very much. Are you able to see my screen, Olga?
Yes, perfectly.
Perfect. So first of all, thank you very much for inviting me to present to such a very interesting crowd. I'm coming from IMEC in Belgium, sunny Belgium, and we are an R&D center focusing on semiconductor technology developments, including CMOS scaling, but we also work on silicon photonics. And when it comes to silicon photonics, we have been developing a few different building blocks that we believe will be very key for enabling what Continental and Heiko actually mentioned in the presentation, these future photonic LiDAR systems. So we're not talking about products that will be in the market in 2-3 years, but rather 5 to 7 years from now. And what I show you here on this is the concept, is really the purpose of developing several building blocks, including integrated lasers, semiconductor optical amplifiers, dedicated IC circuits for control and readout of your point clouds for the beam steering, but also a collection of optical elements that will allow you to do solid state beam steering. And on the receive side here, an array of photodetectors for reading out your signals. So this is an illustration, again, of photonic integrated circuits. Think about this as a footprint of centimeter square, where you integrate the additional components. In this case, the germanium is monolithically integrated. The readout ICs and the 3.5s are hybridly integrated. So we do all this work in our clean room. So we have 2 pilot lines. one that works on 200 millimeter wafers, that's 8-inch, and another one with 12-inch wafers, so that's a 300 millimeter. And in this clean room, we have fabricated for the last years several LiDAR chips and LiDAR prototypes. What I'm showing you here is just one of the latest wafers populated with more than 150 small LiDAR chips that we fabricated recently. And what I'm going to show you now is our results just of 1 month ago. So 1-2 months, very fresh results. We have taken these dies, and after dicing them, obviously, we have packaged them. We've built dedicated PCBs with components, in this case, still discrete components, where we have packaged or wire bonded, in this case, our photonic chip. And the photonic chip is a slightly different architecture from the one you see here on the left side. But we have done so in order to demonstrate. We've also put together all these components, so the PCBs with the photonic chip, all the dedicated electronics in a custom housing, also a small lens there, and this lens is indeed for the imaging part. And with this in the lab still, we have obtained our first point clouds that you can see here. Again, very, very early results that I wanted to share with you guys that we have just obtained in the last month and a half. And that's what I wanted to share with you. I'm open for questions. Thank you.
Thank you, Marcus. So how about, the challenge from Zach? 1550, very extremely robust FMCW. What do you say? I already challenged Matidia. How about you? What would you say? You're
Exactly.
the iMac.
So that's a good question. So indeed, what I showed you here, this is done at 1550 nanometers. Okay. So we are working at these longer wavelengths. Was just mentioned by John Deere that typically longer wavelengths tend to penetrate better fog and particles. There's obviously a limit that was also mentioned, but we have been working on 1550 at 1310. So that's the O band. We are exploring indeed these longer wavelengths. Now, what you saw there and what I showed you first is the first prototype, and this is what I would classify as a short range LiDAR, talking about maybe a few tens of meters in range. Next iteration will be what I call a midterm LiDAR that will be up to 100 meters still in these wavelengths that I just mentioned, O band, C band. And then finally, the long range also, as Heiko had classified it before, up to 250, 300 meters. So we believe that working on silicon photonics is really a way to reduce the price, to increase the volume, also increase the robustness of these, assuming that you put everything integrated in a solid state wave and way, and that's exactly what we are trying to do at IMEC. Again, we're not in the business of building a LiDAR per se, but rather developing the technology to collaborate with partners, and some of them that are in this meeting actually. So
are you optimistic on going in January to the North Dakota?
We could go maybe in the summer.
Thank you. Any questions for Marcus? I see maybe in the room. Zach, so does it sound promising to you? Everything, all your parameters are met. 1550, frequency modulated CW. They are ready to go to North Dakota.
But not in January. Yeah, so obviously very, very interesting, right? Yeah, and I think it merits further discussion.
Thank you so much. And so then I will actually introduce our last and not least speaker, and which is actually a very untypical speaker for our meeting. It's a Damon Deal from Luminate or Next Corps. And Luminate is actually accelerator for all the new and modern technologies. So he has an opportunity to already work with the youngsters and see what is coming up. So Damon, now please give us a spectacular ending to this meeting and tell us what are the new what technologies that are now being developed.
Hi. So as Olga just said, so I'm Damon with the Luminate Startup Accelerator, and we are located in Rochester, New York, and we are the largest startup accelerator for optics, photonics, and imaging in the United States. And when we work with all kinds of technologies, and so the specific interest here is that we're recruiting. And I was going to show 3 of our companies that work in this field of ranged imaging in general, and hopefully inspire some companies to have a conversation with me about whether what we're doing might be relevant for you. And the three companies I'm going to be mentioning, and I'm not going to get into detail for the technologies. So we have Preact, Owl, and Voxel. An interesting thing about Voxel, though, is that they have been doing their work with IMEC as far as product design. So that's one connection going on there. Preact is a near field sensing, and so they start off with collision avoidance for automotive. They now do a lot of work with indoor and outdoor work and stuff I can't talk about. Owl technically is not LiDAR. They are doing 3D thermal ranging using AI. So the conversation about hallucinations is always a concern there. And Voxel is doing things that are mostly related to handheld commercial devices. But as far as Luminate goes, like I said, we're recruiting right now. We are a hybrid program. We work around the world. And Voxel, for example, is in Belgium. And I think I will leave it at that because I know we are running over time, but I would love to have follow-up conversations on my own.
But nevertheless, Damon, I have a question. Since you already have, because it's a little bit, like a final touch for the meeting, because we were started it with the question: is there a space for LiDAR, or maybe or no? And since you're working with many young companies, what is your feeling over the years? Is this market increasing? Is it going down? Is it staying stable? New text is appearing. Just your subjective opinion.
Subjective opinion. I'm definitely seeing more. We are seeing more and more applications every year, absolutely, for sure. And there have been migrations out of automotive, for example, and that may be, you look at the iPhone, for example, we may have thought of LiDAR as being the future for automotive, but that is one application that everybody's carrying around in their pocket right now. Preact is a company that started off in automotive. Getting in with these tier one manufacturers is a long game. And so Preact has found some more immediate success with some commercial applications, picking up some of the slack for some products that Intel has dropped. Owl is automotive. However, they also have a lot of work that they're seeing in terms of construction and agriculture. And Voxel is a commercial application as well. So the future is bright, just not necessarily where people thought it was going to be originally.
Thank you so much, Damon. Well, I hope with this optimistic note that the LiDAR will continue. I'm happily closing this meeting. Thank you everyone for your attention. That was amazing to have you around, and I hope we will continue this conversation in future. And of course, I would also like to thank our team from Optica, Elise Fritzcage, our administrator and Marcom, Colin from IT, my peer Helena Diaz Iriegas, the director for lasers, for supporting me, and thank you for all the speakers. It was a pleasure to have you. And now I think the IT needs to close the room and kick everyone pretty much out. Thank you, gentlemen. It was a pleasure to have you. I'm